Good evening, ladies and gentlemen, and welcome to the BRLSI. We are a small group, but I can see immediately of tremendously high quality. And we're going to have a very nice time learning about rubbish this evening. But for tonight, I'm delighted to welcome Dr. Tristan Rees-White, who's from the University of Southampton, but he tells me that he actually spends most of his time WFHing, working from home, and also travelling around and inspecting big piles of rubbish. And I think that he's going to tell you more about that this evening. So, welcome.
Oh, thanks for coming along. I've done enough research in this to know that landfill gas is not the most riveting subject, so I appreciate you coming out on such a beautiful evening as well. So yeah, my name's Tristan. I'm senior researcher at University of Southampton, School of Engineering. I did my PhD at Southampton many years ago, and that was all to do with preventing groundwater pollution from things like landfill sites. And part of that research, I spent a year just up the road in Westbury at the Lafarge cement factory, which I think has been pulled down now. But that was looking at the waste that comes out of these cement kilns, and what the fate of that was. It's all buried underneath the White Horse there at Westbury, so if you ever drive past, it's a big pile of concrete under the ground. So our group at the university, we do all aspects of research into waste, waste management. That's mainly been groundwater sort of based and sort of ground based, preventing groundwater pollution and contamination. We've also been looking at ways to accelerate the cleanup of contaminated sites, not just landfill sites, but other contaminated sites. And then a bit more recently, we've been looking up at the atmosphere and looking at greenhouse gas emissions from the waste industry, which are declining, but they're still fairly high, which we'll talk about later. So we've been looking at ways you can measure them and ways that they can reduce them. So where's my pointer? Yeah, there we go. So a quick plan for tonight. I'm going to talk a bit about greenhouse gases in general, and then emissions from the waste sector, and then look at landfill gas emissions specifically, how you measure them and what can be done about it. So, got to start with a definition. You know this already. It's kind of GCSE stuff, but start at the beginning. What's a greenhouse gas? These are gases that prevent heat from leaving the Earth's atmosphere. Solar radiation warms up the ground. Some of that's reflected back as infrared radiation, and it's absorbed by certain gases, and they heat up, and then that gets re-radiated into the atmosphere, which then over time starts to warm the atmosphere. It's a natural process. It's why we don't live in a big icy ball. Most greenhouse gases come from volcanic processes, weathering of rocks, degradation of organic matter, and that tends to be regulated by plate tectonics and oceans and plant life. But of course, in recent years, we've noticed that concentrations of these gases, these greenhouse gases, have started to increase. And you look back at the records, and it's pretty clear that since the sort of mid-1800s, there's been a steady increase in greenhouse gases in the world's atmospheres. And then in about the 1940s, when we really started to use a lot of fossil fuels, burn a lot of coal, that's when things really took off. And this graph is leveling off a bit now, but we've obviously already made quite a big impact on the atmosphere. There's a trend these days for doing what's called PICO presentations, which was new to me, but you have to do one of these presentations in less than 5 minutes. So you kind of just memorise a few facts, run off. So I'm not used to speaking for so long, so I've actually written out some notes, because and also some of these some of these facts and figures have only just come out recently, so I do apologise for having to read off a bit of paper every now and again. But yeah, so these are the gases, and this is what's happening. There's three main gases which are causing a problem. Carbon dioxide, the well-known one, methane, nitrous oxide, less well-known but quite a significant gas. And then there's a fourth class of gases, fluorinated gases, which there's not a lot of them, but they have really significant impacts. And you know, these are refrigerant gases, and you know, they're used in lots of industries. So compared with carbon dioxide, there's not a lot of it, but it does have a big impact. So how do you compare these gases? Well, we give them what we call the global warming potential. You've probably seen this written down as GWP 100 or GWP 20. And this is a way of comparing different gases which absorb heat in different ways, and then normalising it all to carbon dioxide. So, yeah, different gases absorb that infrared radiation, and that's called their radiative efficiency. And then depending on the type of molecule, depends how long it stays in the atmosphere for. So for example, methane has a very high radiative efficiency, much higher than carbon dioxide, so it will absorb a lot more radiation per molecule, but it only lasts in the atmosphere for decades, whereas CO2 will stay in the atmosphere for centuries. So they do these calculations and say, well, over 100 years, how much methane, how does methane compare to CO2? And then they normalise it, and they normally talk about tons of carbon dioxide equivalent. So when I'm talking about methane, you'll see it written as carbon dioxide equivalent. And then these are the values that tend to be used for the global warming potentials. So it's really a value of a measure of how much more impact certain gases have compared with carbon dioxide. For methane, it does vary depending on the study. No one can quite agree, but for methane, over 100 years, sort of 25, 30 times more impacts than CO2. Nitrous oxide, much higher. And then these fluorinated gases, as I said, there's less of them, but they might have 20,000, 25,000 times more impact than carbon dioxide. I'm talking about the GWP 100, because that's the most common way of talking about these. And for methane, the sort of standard number that's used is 28. So when I'm talking about methane, you times the mass of methane by 28 to get the carbon dioxide equivalent. Okay, so the inventory, where's all this gas come from? So the UK is legally committed to reducing our emissions, just net zero by 2050. And this was set in law, 2008 Climate Change Act. And this is all about reducing the gases emitted to the environment and reducing the amount of gas in the environment. So it's like a two-pronged approach to meet net zero. The reduction is based on targets, the reduction targets are based on levels from 1990. So that's where everything starts on 1990. What are we doing since then, and where have we got to? This little graphic here tells you roughly where the biggest impacts are. We'll come back to that in a minute. But this is what we're looking at: energy, which includes power stations, transport, is including energy, heating, agriculture, industry, waste, of course, and then land use. So, where have we got to? The greenhouse gas inventory. So every year, the Department of, let's get this right now, Department of Energy Security and Net Zero produces a greenhouse gas inventory for the UK. This was released just a couple of weeks ago for 2024. It's a preliminary, and they'll check all the calculations, and then the final results will be published probably later in the year. I can't imagine it will change very much. And it shows that in the UK, 2024, the total greenhouse gas emissions were about 371 million tonnes CO2 equivalent. So that's including methane, nitrous oxide, and all the gases together. Sounds quite a lot. We have come down quite a long way. there's been about 55% reduction since 1990. That's mainly been driven by the reduction in use of coal in power generation. And then last year, you probably saw in the news, they turned off the last coal-fired power station in the UK. There's talk about starting them up again, but it was good for a while. There's a lot more renewables which don't produce much carbon. And then in recent years, we've closed all the blast furnaces in the steel industry. Although I did see on the news tonight that we've now got this tariff deal for metals, so they might fire them all up again. So things are going in the right direction. We're going down. It's a bit slower than I think everyone wanted, but it is at least going in the right direction. This is a mix of those gases. So out of that 371 million tonnes, about 80% of that is from carbon dioxide and about 15% methane. So how do we compare with the rest of the world? Hello, wrong direction, excuse me. So we're down here, 370 million tonnes CO2. This is data from 2024. Some of the countries, it's a bit out of date, and you might want to question their accounting on some of this, but it's good for comparison. You can see the states up there, they're at nearly 5,000 million tonnes, and then you can't see China because I'm in the way, but they're about 13 gigatons, so 13,000 million tonnes. So you look at that and you think, well, we're not really producing that much in comparison to the rest of the world. We're fairly average for a Western European country, but we are still producing nearly 400 million tonnes of gas from a relatively small country, which is why we're interested in it and why we're trying to reduce it. And another thing to realise is that the UK, we get a bit of a bad press for these things, but we actually are on top of this and we are pushing it, which a lot of countries aren't. And countries do look to us to what we're doing. So, changes we make here will follow down the line, and China will start implementing some of them, hopefully in the next few decades. So, territorial UK emissions, 371, and this is how it fits by sector. So, domestic transport is currently the highest emitter of greenhouse gases in the UK. It used to be power supply, but renewables have really made a big impact, and that's still going down. Agriculture is significant. We're a nation of farmers, and agriculture is still a problem. Lots of dairy farms in the UK, which aren't very good. So, they're looking at ways to reduce that. And waste is down there on the right, about 20 million tonnes a year, about 5% of the total. So, it seems relatively small, but, that's what we're talking about tonight. And waste includes landfill, wastewater, so water treatment plants, incineration, composting, anaerobic digestion, and mechanical biological treatment, MBT. The last two are ways to produce biogas from wastes. So it does exclude incinerators that generate electricity. So there are incinerators which take waste, burn it, generate electricity. That's included in the power supply. And one last thing is, out of that 90 million tonnes, 91% of that is methane. So that's kind of what we're going to be talking about tonight. So this graph shows emissions from the waste sector since 1990. And as you can see, it's been quite a big reduction, 70% since 1990. And that was mainly due to the introduction of the landfill directive in the 90s, which made permitting mandatory, and also every permitted landfill had to have a management plan for managing gas and leachate, which is the liquid pollutants that come out of landfills. That was implemented. That's regulated by the Environment Agency, and so all these landfill sites had to install gas infrastructure to collect that methane. Before, it was mainly just venting to atmosphere. They also realised there was a lot of money in it, so they now burn that gas to make electricity, which we'll come on to in a minute. This breaks down to the different parts of the waste sector. As you can see, the brown line there, most of it comes from landfill. and wastewater treatment is fairly high. If you zoom in on that, the bottom level there, you can see wastewater treatment hasn't really changed much in the last 30 years. Some of these other ones are coming up, composting, you know, I don't know what they do in Bath, but certainly where I live, all your food waste is collected, all your garden waste is collected separately, and that either goes to anaerobic digestion, which they put in tanks, sealed tanks, they collect the methane and they burn it to make electricity. And the same with composting, you know, that's taking a waste material and putting it back as a useful product. But yeah, most of it is landfill, and so that is what we're going to talk about tonight. Okay, so another definition. What is a landfill site? I'm sure you know, but you know, we'll run through it quickly. Two types of landfills, permitted and non-permitted. Permitted just means they've got a permit they've got a license to tip waste. And these are post-1995, after the landfill directive came in. Non-permitted sites, also called historic sites, they are pre-1995, where it was all a bit lawless, it was a bit Wild West. You know, if a farmer had a field, he could just dump whatever he wanted in it. And they did. There's some pretty awful things happened. Permitted sites, there's about 2,000 in the UK, 2,000 permits for landfill in the UK. Only about 540 are operational. So the other sort of 1,500 are either completely closed, restored, there might be country parks, or they're mothballed, which means they're closed, they're not taking waste, but they might reopen if enough waste comes along. This is probably what you think of when you think of a landfill, if you ever do think of a landfill. But modern landfills are very well engineered. They have bottom liners to stop leakage from the bottom. They have drainage to collect any pollutant that comes out. The waste is put in layers, and as it fills up, it's capped with a sort of impermeable plastic membrane, and then to catch and that stops water getting in, and it also prevents the gas from just coming out to the atmosphere. So to collect the gas, they install wells in the top of that, and then they draw that off and take it to a power plant or a flare. A couple of pictures of landfill sites. One up there in the top left. This is obviously a nice restored area, and this one's still being filled. This is fairly typical of a modern landfill in the UK. This is about, I think, 80 hectares size, so it's decent size. This is the old bit, it's all being restored, you know, there's nothing much there, there's sheep grazing on it in the summer. But it's his active cell, and then the black bit there is the bottom liner, and the idea is that they'll fill this kind of gap in the middle, fill the hole up, cover it over with soil, and then walk away from it. Obviously, the monitoring of landfills goes on for decades, maybe hundreds of years. This is, it's an active site, you know, trucks driving around with waste. And then this is obviously a bit of an older one. This is a permitted site. That's now a nice country park with paths, and you wouldn't even know it was a landfill. These are some active landfills I was working on recently. This shows the plastic liner at the top, and then they're covering it with soil. And then you might be able to see these pipes sticking out of the ground. There's a few of them dotted around. And then you can see a couple in this picture too. That are gas pipes that are drilled in through the surface, and they kind of take that gas off and then send it to a power plant. And this site here, as you can see, this is been filled up probably in the last 10 years. And then what they'll do is they'll then start filling this area here until it's nice profile back down to the ground level. So permitted sites. As I said, there's also a lot of non-permitted historic sites. These are, pre-landfill directive. In England, there's no data for Wales, Northern Ireland or Scotland, but in England alone, there's records of 20,000 of these historic sites. There's loads of them. Records go back to sort of 1930s, 1920s. Some are known to be older than that, back into the 1800s. But yeah, 20,000 of these, and you add up the area, and it's about 1% of UK land use is old landfill sites, which is a bit mad. These are designated vacant and derelict lands. People don't do much with them. There's a couple of photos here. They just tend to be pasture, open fields. They're not really used for agriculture because no one's ever too sure what's underneath it. Sometimes they use as playing fields. Some are just left to go back to nature. This is actually a landfill site with a big woodland on top of it. And some, if they deem it safe enough, they will start to build on it. This is a housing estate being built across this old site here. They have to do very extensive monitoring to make sure there's nothing unpleasant coming out, particularly gas. You don't want gas building up in your basement. And where does this gas come from? So, you dump your rubbish, well, you chuck your rubbish in the bin, it goes off to a landfill, and that contains organic matter. And under anaerobic conditions, that will break down and produce methane. So it has to be anaerobic, like no oxygen. And that can take several years to kick off. So for the first 3 years, nothing much happens, and then the methane starts to increase. And after about 10, 15 years, these landfills are producing loads of methane, and it peaks at about 20 years, and then there's a long decline. And the decline in methane production goes on for decades. We're monitoring sites that are 100 years old, and there's still methane coming out of the ground. So it doesn't just end when you walk away from the landfill. And again, this is quite interesting. 20,000 landfill sites, about 30% of the methane measured from the waste sector comes from these old sites. And they're just sitting around, dotted everywhere. They're all around Bath. Anywhere there was an old industry, there's these sites pumping out methane. So, where have we got to? Okay, landfill gas monitoring. How do we know where this, how do we know where these figures come from? Where do they get these values, this 371 million tonnes? Well, you have to measure it or estimate it. And currently, we estimate emissions using models. And the model that is used is called MELMOD, and it was developed by DEFRA, the Department of Environment, Food and Rural Affairs. And it's a national model that looks at the waste streams that have gone into the ground since records began, which is approximately in the 90s. There are records going back older, and some of the records around the 90s are a bit sketchy, but that's where the records begin. That's where people had to log what was going through the gates onto the landfill site every day, the volume and the type of waste that was going in. And then they use biodegradability factors to work out how much of that waste gone in is going to start producing gas over time. It's what's called a first order decay model. That means sounds complicated, but it just means as the waste degrades, the amount of gas it gives off decreases over time. Sort of shown on this graph that waste from the 40s is giving off a lot less gas than waste from the 2000s. As it works on national level, it's not site specific. They just add up what they think is coming in every year, and then what's come in previous years, and then using these EWC codes, these European waste codes, which have come from experiments that have been done in labs here in England, and they just know from these batch tests what sort of gas is likely to come off, but it is an estimate. It looks at methane capture, so they drill the wells, they suck the gas out, goes off to a gas plant. That's measured very carefully, and that's then deducted from the amount of methane that's produced by the landfill. And it also includes soil oxidation, and that is methane oxidation in the top soils of the landfill. So as the gas passes up through the soils, it gets oxidized by methanogens, natural methanogens that live in the soil, turn to CO2, and that's again deducted from the total. They use this kind of generic 10%, but the research we've done shows that 10% is a bit of a plucking it out of the air sort of thing. It's very seasonal, very dependent on the soil type. Methane oxidation needs moisture, so it actually works well in the winter, but also doesn't like being cold, so it dies off in the winter. MELMOD, the model, is also national. It's not site specific, and of course different sites will be collecting different types of waste depending where in the country you are. Industrial areas tend to have much more commercial waste than rural areas. And the biggest bugbear I have with the model is it doesn't use empirical data. It doesn't use actual measured data. You know, there's these values they've got from 10, 15 years ago, they're still using. And everyone uses these, you know, everyone in Europe uses them, the IPCC uses them all around the world. But no one's ever said, if we calibrated this model, we actually taken, you know, real data to see if it fits. And that's what we're doing. That's what I'm going to talk about a bit in the middle. So how do you get empirical data? How do you measure what's actually coming off these landfill sites? This is the traditional way of doing it, flux boxes or walkover surveys. A flux box is basically a big bathtub, you turn it upside down, seal the edges, and you monitor the concentration of the gas inside the box as the air kind of gets taken over by the methane that comes out of the soil. It's fairly cheap and cheerful. It works, it's not that accurate, they leak, and you know, if you put it down in the wrong place, you might miss the gas. Also, you're only measuring, you know, sort of metre square or something of landfill, and some of these sites, this one here in the corner is, you know, 300 hectares in size, it's massive. So to get a representative idea of what's coming off this site, you know, you'd be able to do these for months and months and months. You know. Another way of doing it is by walkover, where you take a gas analyzer and you literally just walk around to measure concentrations. Again, it's quite simple, fairly cheap, apart from you've got to pay someone to walk around for weeks measuring it. It's also not that accurate. This was the only way of doing it. It's now not really recommended, because there's new ways, including LiDAR and dial, a bit more sophisticated in a bucket. You have a sensor on a pole and it fires a LiDAR signal down, and it measures the different wavelengths that get reflected back to the analyzer, and from that they can calculate reasonably accurately the concentration of the gas at that point. This was developed for the oil and gas industry, for looking for leaks in refining plants and things. You can see a picture there. If you have a very complicated wind model, you can do a mass balance calculation and work out a whole site emission using this, but it's tricky, and these lasers are quite small compared to, again, you know, that massive landfill site I showed you. So NPL, the National Physics Laboratory, they developed a giant version of this in this big articulated truck, which they can drive around, and this can actually measure you know, right across the sort of plume of a landfill site, or most of it anyway. And you know, they can get actually quite a good idea of what the emissions are. So it's very good for leak detection. It's not very good for whole site emissions, and it does involve a very complicated wind model, which means you're monitoring the wind in 20 or 30 locations around the site, probably at 100 hertz, so 100 times a second for days on end. I mean, it's very, you need a decent computer to work it all out. The big trucks can't access all areas, of course. It's fairly accurate. They have done calibration studies with it, but it's very expensive. So a survey from MPL, I don't know what they charge now, but when they started this, they used to charge about £60,000 for one-off survey. So it's expensive. This is a more modern way of doing it, using UAVs, two types, rotary, fixed wings. Rotary is now the common way of doing it because the technology has improved so much. The analyzers they use are getting smaller and lighter, and less expensive. So if it drops out of the sky and breaks, you know, the analyzers used to cost hundreds of thousands of pounds. Now they're tens of thousands of pounds. And the way they work is they fly them up, and they just fly backwards and forward through the downwind plume of gas from the landfill site. And they create what they call we don't do this at Southampton, we might get into it, but they call it a wind orthogonal flux plane, which basically means a vertical kind of window through the downwind, and then they look at the concentration of the methane. Again, this needs very, very good high resolution wind measurements. And ideally, you want wind measurements from the ground level up to the top of where the drone is monitoring, which is normally about 120 meters. And it's very difficult to get wind measurements, particularly that high. You know, you can put a mast up maybe 10, 15 meters. So they are reliant on wind models, which are, reasonably accurate. And then the computation is very complicated. Again, there's not many people who can do this yet. It's improving. So far, it's not been brilliantly accurate, but it's improving. There are restrictions to UAVs where you can fly them. You're not allowed to fly them over public highways, public property. You can't fly them near airports, near military bases. You can't fly them if there's power lines, if there's tree cover. So there are lots of restrictions for these, but this is where that is the future, as is this, remote sensing, monitoring methane from space. It's not new, they've been doing this for quite a long time now, but GSAT have really taken this forward in a big step. At the moment, they've got 12 satellites up, and they're planning up to 80 satellites, and they'll be spaced all around the globe. And at the moment, even 12 satellites, they have a 2-day pass rate, which means every 2 days, at least one satellite will pass over the same location. And the way these work, they similar to the LiDAR lasers, they just point horizontally down, they fire down, and they measure the column averaged concentration of the gas below the sensor. And the spatial resolution is currently about 25 meters, which sounds quite big, but until a few years ago, it was hundreds of meters. So that's all improving. So you can measure concentrations within a 25-meter square fairly accurately. They say they've got a detection threshold of 100 kilograms an hour. That's based on some model data. Real world data, they're nowhere near that yet, but it's getting there. And the great advantage of this, it's expensive to get them into space, but once they're there, the cost is actually quite minimal. And what these guys do, they work with this team called Spectra, and you can sign up to this for free. Anyone can sign up, and you can ask them to target certain areas. They probably avoid some areas, but you could say, actually, I'm interested in a big dairy farm down in Cornwall, or an oil rig in the North Sea, and they will ask a satellite to target that next time it flies over. And I said the satellites pass roughly every 2 days, so you can get an almost continuous measurement of what's happening. And what you do, you can sign up, you can select a few areas that you're interested in, and it will send you an alert when it gets, you either get a text or an email when something interesting is detected. Now, when I first signed up, I signed up for everything, and it was just pinging. I'd go in the morning, I had like 2,000 emails, because it turns out we're releasing methane all over the planet, quite alarmingly. So now I've restricted it just to the UK, and this came through Monday morning. This is a permitted active landfill site in Northern Ireland, near Port Stewart. And yeah, when they flew over the other week, they detected the methane, and they did the calculations, and they worked out it was about 450 kilograms an hour, which is fairly standard for a landfill site in the UK. This is all very good, but if there was a landfill site next door pumping out 300 kilos an hour, it wouldn't be able to detect it. So it's not quite there yet. It's getting there, but it's not quite there. And then there's what we do at Southampton. This is my big spiel now. So I'll spend a bit more time on this. How are we doing for time? Am I rattling on too long? Oh, we're okay. We call it tracer dispersion. It's got other names: tracer correlation, tracer gas dispersion. Again, this is not that new. It's been used in various forms for the last couple of decades. It's quite popular in America and Northern Europe, but currently we're the only people in the UK are doing it. A few people are getting involved. And this is a whole site measurement. We have a van which will drive downwind of the site. It doesn't have to be a landfill, anything that's producing a gas. And we measure the concentration of the gas that we're interested in, and then we release a second gas, a tracer gas, from the site, and we measure that as well. And then from that, we can calculate the emissions. So just briefly on plume dispersion, gases, stating the obvious, but gas will disperse downwind of the source. Source can be anything. Here I've got a kind of a cartoon of a landfill, but it could be a dairy farm, it could be an oil refinery, a wetland, anything that's producing gas. Doesn't have to be methane, CO2, nitrous oxide, whatever you're looking for. And if you walked along that plume, the further you got away from the source, the lower the concentration you'd measure. And that's because As the gas disperses downwind, it spreads out. And so, yeah, as you go downwind, at any point, the concentration gets lower and lower, something like that. I mean, it's kind of a cartoon graphic. But yeah, close to the source, high emissions, further get away, low emissions, but over a much wider area. And this is a kind of real world example of that. This is a landfill site up in, where's it, Staffordshire, I think. And yeah, these are methane measurements. And you know, we drove along in our van, along this road, measuring the concentrations of the gases. And so this isn't elevation. We're not measuring gas, you know, hundreds of meters above the ground. This is concentration. So close to the site, as you'd expect, concentration is quite high. And as you get further and further away, you know, up 6 kilometers away, you can still measure the gas, but it's, you know, it's much lower concentration. So how does our method work? We drive through the plume of gas, as I've said, and we produce a graph, something like this. It's not always as neat as that, but, and then, there we go, another example. So these are methane plumes measured downwind of another landfill site. We then release our tracer gas. The trace gas we use is acetylene, welding gas, which you can buy from Bock anywhere. It's fairly inexpensive, but it's quite dangerous to work with because it's highly flammable. So yes, a few regulations on using this, but we set up a bunch of bottles, 4 to 8 bottles, depending on the size of the site and the wind speed. And then we release that gas into the atmosphere from the landfill or whatever we're trying to measure. So you then get 2 plumes of gas. The methane from the site, our tracer gas, our acetylene, and when you drive through, you then get 2 curves. And then, there we go, so that's the same one. This is our trace release down here, and the acetylene's the pink, and the methane's shown in green. And as you can see, we're slightly off centre to the site, and so the plumes are slightly off centre. Ideally, you'd want to be in the centre of the site, but this was an active landfill with trucks driving around, so we couldn't be. So how do you calculate emissions on this? Well, you've measured how much methane there is, you've measured how much acetylene there is at a given distance downwind, and because we control very, very carefully how much of that tracer gas we release into the atmosphere, we know what that rate is. We can back calculate the methane. So it's quite a simple thing. It's not complicated, but you do need the right equipment. This is what we use. This is a Los Gatos gas analyzer. It's called an ultra portable. Still weighs 20 kilos, about the size of a suitcase. They do smaller ones now, but and this is the heart of what we do. And it's an off-axis integrated cavity analyzer, which means there's a cylinder at the front here. It's about, I don't know, it kind of looks like a kitchen roll tube. And there's a mirror at each end of that, which is at slightly opposite angle. And then there's 2 lasers hidden behind this black box, and they fire down the cavity of that cylinder, and it bounces off the mirrors. And because the mirrors are slightly off axis, the laser bounces back and forward. So that cylinder is, I think, about 20 centimetres long, but it bounces back and forward so many times, the effective path length is 2.5 kilometres. And because it's so long, it can measure very small changes in gas concentration within that cylinder. So we can measure down to 2 parts per billion at 1 second frequency. We have a pump which draws a sample in from outside the van. We just have a tube sticking out the door, and it sucks the ambient air in into the analyzer. We have a GPS unit on top of the van, which every time we take a gas measurement every second, we also log the location using GPS, and that helps us produce those plots, with those satellite images with the graphs and things on, and it also helps us locate different parts of the plume. Everything's battery powered, 12 volt, so it's all very portable. You can actually get a backpack for this, so you can carry it around. You wouldn't want to because it's pretty heavy. So a couple of photos of the trace release. This is as important as all the monitoring. The equipment's a bit not quite as fancy, but it's just as important. We need to know very accurately how much that tracer, how much that acetylene has been released into the atmosphere. These are old historic sites where it's all grassed over, it's all quite straightforward. This is an active landfill. We had to wait till they went home so we could drive up there. I put these two in, these nighttime shots, because for the gases to sort of travel downwind nicely, you do need a bit of wind. They've got to be blown downwind. But you also need quite stable atmospheric conditions. So the worst conditions are like days like today, where it's very warm and sunny, the ground warms up, and everything just floats off horizontally, vertically, I should say. So we're driving around, measuring, maybe 2 meters above the ground, and the gases are like hundreds of meters above the ground, above our heads. So bright, sunny days, any time of year, aren't very good for this. What we really want is nice cloudy days with nice steady winds. And if you can't get that, we work at night, or dusk dawn on nights when the atmosphere is much more stable. The other advantage of working at night is that the road's quieter, because you are driving around for 2 or 3 hours up and down, annoying the neighbours, flashing light on the van, and it's just a bit quieter at night. Some of the results, what things look like. So this is these are all landfill sites. This is one in Suffolk, I think, and we measured about 100 kilos an hour from this one. Can't remember what this one is, but slightly, about 90 kilos an hour. And this is the one I showed you earlier. This was a bit high, it's about 250 kilos an hour. They had a problem with their gas engines, and all the gas engines, which would normally be burning the gas, were turned off for servicing. So emissions were much higher at this site. And we went back a few weeks later, and it was all about half of that. So every time we drive through and measure the gases, we calculate an emission flux, which is what all these data points are. And so this, I can't remember when he did there, maybe like 15 or 20 or so. And then we take the average through there. And we do a bit of statistical analysis to take out any outliers. And there's a bit of work looking at these graphs, because sometimes you'll drive past a dairy farm or a big pile of manure at the side of the road, and you measure a big spike in methane, which of course offsets what you're trying to measure from the site. We haven't just done active sites, we've done a lot of work on these old historic sites where gas emissions are much lower. This is in Oxfordshire somewhere, I can't remember where, but Wallingford, I think. And an old site, it was closed in the 80s, not very big, but there was a bit of methane coming off it. Because the amount of methane coming off is much, much lower, about 2.5 kilos an hour compared with 250 kilos an hour, the previous one. There's more noise, and that's because there is a background concentration of methane in the air, just natural background, which is about 2 parts per billion. When you're in the countryside and there's lots of agriculture, that tends to be a bit higher, a bit lower by the coast. And so when there's not much excess methane from the landfill above the background, it's much, much harder to measure. So there's much more noise in the data, but we still got a reasonable average of about 2.5 kilos an hour. Technique's not perfect. There is a margin of error in it. We've done a lot of work on this with controlled releases, where you're not just releasing methane from a landfill, you're releasing it from a known controlled source, so you know how much methane has been done. These are blind trials, so we can actually calibrate the system correctly. They've shown that it's about 10-15%. We tend to run up to 20% just to give the margins a bit better, a bit more confidence. There's also a lower limit what you can measure. Some of these old historic sites, there's so little gas there that it's actually quite hard to detect at distance. And we don't really know what the limit is yet. And as I said, sometimes you think you're measuring gas on a landfill or a leaking natural gas well, whereas actually it's a pile of manure by the side of the road. And when you get back to the office and you're going through the data, it makes no sense at all. And then you go back up and have a look, and there's just a big pile of cow manure. And although the methane coming off a pile of cow manure is much less than it would be from a whole landfill site, because you're very close to it, the concentrations are very high, and so you get these big spikes. So it's not perfect, but it's good, and at the moment it's probably the best, with the most accurate method for measuring whole site emissions. Okay, nearly at the end, don't worry. What can be done about all these emissions? We're measuring them, we know they're there, they are going down, but what do? Well, to get a permit for a landfill, you need to have a gas management plan. You need to be able to demonstrate that you're collecting as much gas as is possible, and then you're not just collecting it, but doing something with it. The best thing to do is burn it for electricity, make lots of money. If there's not enough, you can flare it, or if there's too much to burn. Some of this data is a bit out of date, but yeah, we were up to about 3.5 terawatt hours from landfill gas generation. There we go. It's declined in recent years. That's because the sort of waste we tip now has changed. A lot of our organic waste gets composted, doesn't end up in landfills. And there were some very nice tariffs for renewables, which are being taken away in the next few years. So they're saying they're going to take them away. And so there's less incentive to invest in new infrastructure and engines. So it's not cheap to do this. That's what a gas well looks like. It's just a well into the ground. And then the hose goes off, often buried, and then they go off to one of these plants where they suck the gas out of the ground and burn it. If there's not enough to generate electricity, you can flare it. And these are high temperature flares, so it just gets oxidized to CO2. And if it's very, very low emissions, there are low calorie flares, which run at very, very low concentrations of methane, and oxidize it, and again, send it to atmosphere. The trouble is these tend to be on very old sites where the infrastructure is all falling apart, so they don't work very well. Another option is just let nature do its thing. This only really works on older sites where the emissions aren't very high, and they're also unengineered, and there's no plastic liners on the top. And yeah, just let the gas passively vent out the ground, and natural methanogens in the soils will eat up the methane, turn it into CO2. Problem sorted. You can either cover the whole site in soils or have what they call windows, where the gas is kind of funneled to certain areas, which you can then maintain better. This is quite common in Northern Europe, particularly in Denmark. They do this a lot. They have lots of small landfills which have a lot of organic waste from agriculture in, so producing quite a lot of gas, even though they're quite old. And yeah, this is quite a simple, cheap solution. I won't go into this in that much detail, but they've done calculations that, in our sort of hemisphere, our latitude, we can actually naturally oxidize almost all the gas that will come off an old site. We just have to go in and get it ready. So it seems a bit of a no-brainer, but we just don't do it in the UK for some reason. The other thing is tree planting. This is a landfill site, an old landfill site, which they planted trees on back in the 80s, and now it's this big forest, and it's a nice place to walk your dog. But as you're walking along here, there's bits of plastic sticking out the ground, and bottles and things. But trees grow well in a landfill. They like it. I guess the ground's fairly warm and undisturbed. The government pledged to plant 7,500 trees per hectare every 5 years in the UK, and they were going to increase that to 30,000 hectares of tree planting per year by 2030. They are nowhere near that at all. And one reason not near that is because they didn't have enough land to plant the trees on. So as I already said, these old historic landfills, of which there's tens of thousands, are considered derelict land. You can't do much, you can't use them for agriculture, you're not really allowed to build in them. So plant trees in them, they're not used for anything else. Tree planting is great. Carbon sequestration, as the trees grow, they suck up carbon from the atmosphere. Rewilding, biodiversity, air quality, there's so many good reasons to plant trees. And there's also some evidence that planting trees in old landfill does actually oxidize the methane in the soils around the tree. If you compare this to an open field, in the summer that open field will dry out, whereas here the soils are shaded by the trees. There's a sort of continuous supply of organic matter from the leaves dropping down. The roots help bind the soil together so it doesn't crack in the summer. So planting trees in landfill is an option, and they are trying it. This is a site near Bristol Airport. It's quite a small old landfill, and they just went in with this big, what do you call it, plough, to decompact the soils, and then they planted just thousands of trees. This was a couple of years ago. So I haven't been back there, so I'm not sure how well the trees are doing. But apart from some fairly minimal management as the trees mature, yeah, it's a good option for some of these old sites. when I was writing this yesterday, doing a presentation, I was thinking like, oh, how good are trees actually for sucking up the gas? So I did a few calculations. So it's a slight aside, but I thought it was quite interesting. So I looked up how much carbon do trees actually take up a year. Lots of different estimates, and the average was about I didn't spend loads of time on this, but it's about 5.5 tonnes CO2 per hectare per year for new tree growth. So I said, well, okay, this 1% of UK land use is 84,000 hectares from old landfill sites. Let's assume all of them are available, there's nothing else on them, and you planted trees all over them. That's a potential for nearly 500,000 tonnes of CO2 a year. Sounds quite a lot, but it is only 2.5% of this 20 million tonnes of, and obviously we can't plant trees in all of it because that's just not feasible. I then went one step further and said, well, okay, let's assume everyone moved out to the UK, we dug up all the roads, filled in all the lakes, flattened all the cities and just planted the entire UK with trees, sort of like 250,000 kilometres. How much will that suck up? And it comes out about 130 million tonnes a year, which is about 30% of the total greenhouse gas emissions from the UK. So trees aren't the answer. We should plant more trees, and I think they're used as a bit of a smokescreen. So carbon offsetting by planting trees and things all sounds very good, but it actually has a tiny effect. And also, this is for new tree growth. Once trees mature, they actually slow down, they stop sucking it in. So we do need more trees, obviously. We need to plant more trees, but it's not going to sort out this problem in the UK. And one final thing, and then I'll finish. Waste streams are changing. As I said, a lot of our organic waste is now going to composting and anaerobic digestion plants to produce biogas. More and more of our waste is being recycled, and recycling is improving. The way they can take the materials out, split them up, and the way it works, the waste, your black bag or whatever it is, will go to the processing plant, and they run it through trommels, which are big, like horizontal cylinders with holes in that rotate, and as it goes through, they sort the waste into different fractions. So they can take out the metals, take out wood and things like that, and then they can also sort it by size, because certain incinerators need certain sizes of plastics. But as it goes through these trommels, all the very fine grain stuff drops through and lands on the floor, and these are called trommel fines. And even though you don't think there's probably much sort of small dusty matter in your domestic waste, there's actually quite a lot, and it drops through, and those trommel fines, you can't do much with it, so that all goes to landfill. And one issue with that is those trommel fines are very high in sulfates and gypsum, and the gypsum tends to come from plasterboard. You shouldn't have plasterboard in landfill, it's not allowed, but it just ends up in there because people either do it illegally or they just put it away and no one notices. So gypsum plasterboard is becoming a real issue, because what happens, it goes into landfill, it mixes with organic matter in landfill, and it produces hydrogen sulfide. This has always been a bit of an issue in landfill, but it's now become a serious issue. And I'm sure you've seen, let's get that, headlines like this. There's more and more of these coming up. And there's these big landfill sites that have been there for decades, never caused a problem. And now, because of the type of rubbish we've thrown away, it's causing a real issue. And this is Fleetwood up in Lancashire. It's been in the news recently. Terrible issues with odours. This is Hordswood in Kent. This is an illegal tip. People have been dumping stuff there illegally for decades. I'm not quite sure how they've got away with it, but it's just this huge area of the woods. It's been covered in waste. It's completely saturated with rain, and there's loads of demolition waste being put there. So loads of this gypsum board, and it's absolutely vile. 2 miles away, you can smell it. It's horrible. And also, it's a legal dump. So who's going to clear it up? The local council. And Wally's Quarry, you've heard of Wally's, this was in the news a lot in recent years. This is in Staffordshire, near Newcastle under Lyme. Active landfill, not a particularly big one, but the prevailing winds in this area come off the Pennines and they kind of flow down over Newcastle under Lyme, and basically all this housing is downwind. The landfill, which started to produce quite serious hydrogen sulfide emissions about 5-6 years ago. The WHO guidance is for a maximum of 5 parts per billion over 30 minutes. Well, when we were there for about 2 minutes, we measured 150 parts per billion. I mean, it's insane, right, how they got away with it. The local community clubbed together and they took the Environment Agency to court over it because they said the Environment Agency wasn't doing enough to prevent it. They lost that. There was this judicial review, and yeah, the Environment Agency won, and they said they'll just put pressure on the landfill to change their practices, which they did, but nothing really changed. And then I read recently that it's now been closed and they're not allowed to tip waste there anymore. What's there is still giving off hydrogen sulfide, so it's still not a particularly pleasant place to live, but at least they're not taking any more in. And that's it, there we go. Bit of a fast run through landfilling in the UK. So yeah. Any questions?
Thank you very much. You happy to answer some questions?
Of course, yeah. I'll try anyway.
Right. Now, I'm just going to remind everybody that we're not the only people with an interest in this. There are also some listeners and viewers online, and so that's why we have to use a microphone. But the first question from the audience here.
Okay, does substituting energy from waste for landfill for non-recyclable waste address these issues, or does it just swap one set of problems for another? And how does best practice energy from waste compare to best practice landfill?
I mean, I suppose if you're burning the methane to generate electricity, or burning rubbish to generate electricity, that's better than burning coal or oil to generate electricity, because the material's already been dug up. The oil has already been turned into plastics. It's very highly calorific. You can bury it in the ground. It's going to sit there for 100 years, or burn it. It's a fantastic energy source. So yes, it is better, but it still produces greenhouse gas emissions. You're taking methane and turning it into CO2, or you're taking the plastic and turning it into CO2. So yes, it's better than letting it vent to the atmosphere, but it's not the solution. Also, there's not enough, and as I said, waste streams are dropping off. Lots of landfills are closing because there's not enough rubbish to go into them. Incinerators have been shut down because there's not enough to burn. So, every now and again we import waste from other countries to burn, just to keep the furnaces going. So I think for energy, renewables is clearly the way forward, and this is a bit of an interim to sort of bring down the fossils.
Okay.
I mean, did I answer that? I wasn't sure if I...
So I'm not sure whether you said which was the best in terms of greenhouse gases alone, which best practice method is better.
So it's a slightly confusing thing. If a landfill generates CO2, that's not part of the greenhouse gas inventory, because that was grown as, let's say it was a vegetable that was grown. So it's almost like the CO2 cycle. So that's not part of the inventory. So if it's just left in landfill and oxidised and turned into CO2, that is not considered a greenhouse gas, even though it is a greenhouse gas. It's not part of that inventory. So in that way, you're not adding things to the environment. Methane is considered because it's so much more potent. So I still haven't answered your question because I don't really know the answer.
Okay.
Yeah.
That was very interesting, thank you, genuinely. I didn't know anything. My pictures of landfills were this rather than the ones that are covered and then eventually end up being used in nature
Most of them are
reserves,
quite nice
so,
now, yeah, they're actually quite
For your slide about the trees, I was wondering if you took, say, the trees over 100 years, like you did for everything else, whether it would be different, because usually what they do is they unfortunately cut down the trees, use the wood so it's not burnt, so the carbon is still stored, and then plant new ones. So I'm wondering if you took that into account, if it would be better than 2.5%?
I did, briefly. I mean, I only did this yesterday, so just a sort of back of the envelope thing. I did, and the trouble with trees after, I can't remember how long it is, that they stop drawing in as much carbon. So it's quite a lot early on as they're growing quickly, and then it slows down. So over 100 years, the amount they sequester is actually quite small. It reduces over time. And then, you know, if you're then taking that fuel and burning it, you're then, you know, if you burn it for fuel, and there are biogas plants in the UK where we import wood from Canada, which is mad. If you're burning it, then it's like a circular, which is what net zero is all about. It's not just about preventing it going to atmosphere, it's about taking what's in the atmosphere and putting it somewhere. So if you can kind of circulate it by growing a tree, burning it, growing a new tree, burning it, you know, that does improve the cycle. But yeah, people have looked at this. I haven't in detail. So yeah, I'm probably not the best person to answer. But yeah, the other thing I did do is look at the cost of it, because obviously there's a cost involved with planting trees. You've got to get the soil ready. You might have to bring in new soils to build the ground up, particularly on old landfills where the waste is poking through. And I did a very quick cost analysis on biocovers, the soil covers, where you just let the gas come up through the soils and oxidise, and trees. And I don't have the values here, but it was about 1/10 of the price of, you know, this is carbon traders, and they kind of trade carbon from tree planting, forest planting. It was about 1/10 of the cost of, and that was over 100 years of, carbon trading. So I think carbon trading was about £65 a tonne, and this I worked out very roughly over 100 years, because once you've done that initial cost, there's no real further cost. So I worked out it's about £6.5 a tonne that you could sequester. So.
I should just say to those people who are watching online, of whom there are quite a few, if you do have a question, if you would type it into the chat on your Zoom screen, that would be great, and I'll be very happy to take that question. I'm monitoring the chat here. Are there more questions in the room? I have one, actually. Seems to me that there are some rather strong analogies between what you're doing in tracing methane coming out of landfill and what I might do in my house if I were monitoring drafts and heat loss from the inside of my house. I would get a thermal camera and I would look for the hot spots. But what I would do then was I wouldn't worry so much about how much heat was being lost from that hot spot. I would fix it. You know, when I saw those satellite pictures that you had there of methane coming off landfill, I thought, well, gosh, that's really just like what I would do with my thermal camera at home. What we need to do now is to follow up those satellite pictures and go in there and fix the problem. Is that going to happen, do you think? Will those satellites going all around the world find places where methane's coming out?
It will only happen if there's an incentive to do it. So if you're an operator, and operators don't make a lot of money these days, they used to be a very good industry to work with, not so much anymore, costs a lot of money to run a landfill. So if you're an operator, what's the incentive to, well, one incentive is to capture it and generate electricity, because electricity's got a value on it, although those tariffs, as I said, are changing. But that doesn't, involve quite a lot of investment of infrastructure. Or it could come from the regulator, and the regulator says, you can't do this anymore. You're releasing these gases, we've measured it, we know how much there is, and this is one reason for actually quantifying it, measuring it, not just seeing it's there, but measuring it, because then you could then monitor change. So you could say to them, you've got to halve your emissions over the next 5 years or something, and then satellite or us or whoever can go there and check they're doing it. So you need an incentive, and there's not. At the moment, the DEFRA and Environment have been saying, for as long as I've worked in this industry, that they are going to regulate emissions from landfill, and they still haven't done it. It'd be great for us, because then we get loads of work out of it, so it would fund all our research. But yeah, as yet it's not happened, and it's not happened in Europe. Like it's not. There's no incentive behind it.
Yeah. So I could imagine a future in which the satellite was the first stage, and you have someone on Millbank in DEFRA whose job it is to look at what the satellites are finding, and they say, oh, well, actually there's something happening over there in Northern Ireland. We better go and find out what's really happening on the ground. And then they send out the letter that says, we'll close you down if you don't fix this. Yeah. I mean, do you think that that's going to happen, or is it too complicated?
I don't know why it's not happened. Yeah, I'm sure it is complicated, but other aspects of landfill are very heavily regulated, so I'm not sure why emissions aren't. There might be a good reason that I just don't know about. But and the thing with methane, it's odorless, can't smell it, it's colourless, can't see it, so you don't know it's there. The guys living next to that site in well, the three I showed you with the hydrogen sulfide, there's also loads of methane there. They can't see that, can't smell that.
Yes.
They're only complaining because they can smell the hydrogen sulfide. So maybe one good thing about this waste stream changing, this odours have become more of a problem, is if enough people complain about it, they will do something about it. So yeah.
And maybe I could just follow that up by saying, I just named DEFRA there. It's probably not their responsibility, is it? Whose responsibility in government is it? Is it local government?
No,
is it the Environment Agency?
Yeah, it's regulated by the Environment Agency. Yeah, which is part of DEFRA. So it's DEFRA. I
see.
Yeah. So the Environment Agency is funded by DEFRA.
Yeah.
So yeah, the landfill regulation is through the Environment Agency.
Okay.
Yeah, just picking up on what you've just been saying, Stuart, surely the problem is that some of those sites were in other countries, so unless they signed up to your satellite police, then nothing's going to happen.
Yeah, I mean, what I didn't show, because I couldn't find an image of it, is I had an alert a couple of months ago, one of those satellite alerts. So the site in Northern Ireland was pumping out about 450 kilograms an hour. The other sites I showed were about 100, 200 kilos an hour. There's a site in Indonesia, a landfill site, that was pumping out about 12,000 kilos an hour. So again, the scale is completely different. And you're right, it's completely unregulated. There's no one's going there and telling them to, stop doing it. So
where was that?
It was in Indonesia somewhere. I can't remember. Yeah.
Because we're shipping, aren't we?
No, we ship recyclables, but we don't ship domestic waste. We ship it to the Netherlands, because Netherlands stopped landfill completely. They've got lots of them, but they stopped a new landfill. and they built loads of incinerators, but they're not producing enough waste to keep them running. You have to keep these furnaces going. It costs so much to shut them down and turn them back on again. They have to keep them running 24 hours a day. And they don't have rubbish there. They're buying our rubbish to burn there, which meant we didn't have enough for our incinerators. So they were buying our rubbish, and then we were buying rubbish from France and Germany. It's just mad. Shipping rubbish from Germany to here because we ship to I mean,
It's quite extraordinarily interesting. Do we have any more?
I mean, I have a lot of thoughts forming in my head. I'm not sure. One thing that I wanted to mention is you were talking about values, monetary values. So, what values has nature got, and Mother Earth, and the value that it is providing everything we need, surely, if we don't have Mother Nature anymore, that's the end of human existence.
I mean, you saw some of the photos of the sites that are closed and being restored.
Yeah.
They are wildlife havens because you can't build on them because the ground's too soft and it's uneven and there's gas and you can't build on it. So actually, it's just left to go back to nature. So actually, old landfills, even active landfills, are incredibly biodiverse. Like surprisingly, even like ones like this, they'll have lots of bird life, predatory birds, lots of foxes, and all sorts of animals around them. So yes, surprisingly, landfills are incredibly kind to nature. Surprisingly, so that is a good thing. Can you put a price on it? No, of course you can't. And like the planting tree thing, we were doing it as research. Does planting trees in landfill help in any way? But the obvious answer is it doesn't matter because we should be planting more trees. It's just is there like an added benefit apart from rewilding and biodiversity? So yeah. But then, unfortunately, I think the world we live in, if you don't put a value on things, people don't do it.
Yeah.
So.
Yeah, it's all about power and money,
Yeah.
like always.
Exactly.
Yeah. And is there anything that can be done about the sulfur at all? I mean, I imagine if there was, then it would have been done by now.
Yeah, well, you can. You can collect the gas, so you can collect as much gas as possible, and then less of it gets blown downstream. But the trouble with hydrogen sulfide, it's you can smell it. It's such a tiny. Like some people can smell it at 0.5 parts per billion, which is, it's insane. Like there's instruments, analytical instruments can't do that. So we're very sensitive to it. So it's very hard to get rid of all of it. So the site in Staffordshire, they had to put in loads of gas infrastructure, pump lots more gas out, burn lots more gas. They were flaring it. They weren't generating electricity. They were just burning it. That helped. Didn't take it away. You can put chemicals in the ground, which help kind of neutralise it, but it's very expensive, and you are adding something else into the... you could lower the water level because all these processes do need quite a lot of moisture, so you could dry it all out. So there are things you can do, but it's actually quite hard to get rid of all of it unless you just cap it, stop it coming out. So... Yeah.
That's possible too.
That is possible, but it's expensive. So, and like, when we were working at Wally's Quarry, Staffordshire one, that was all in the news, it's this big new housing estate where people are having all these problems, and there's people like reporting a lot of health issues as well. And then right next to it, they were building an even bigger, like hundreds of new houses right next to it, and it's like, well, don't build them there. Like, there's a problem, but they're building new houses and people are buying houses and they can't sell them, of course. So it's a bit crazy, I don't know. Yeah.
So and I didn't quite understand how this sulfur comes into existence.
So, it's in the gypsum plasterboard, and there are sulfates and other types of waste. And then, I mean, I'm not a chemist, so I don't know exactly, but when you mix it with organics, you can get sulfide reducing bacteria, and that basically eats the sulfur and converts it to hydrogen sulfide. So it's a bacterial process, it's a microbial process. It's, yeah, I'm sure it's more complicated than that, but that's sort of,
Yeah, thank you. I've always been interested in, you know, in waste and where it goes once it leaves the house. And I absolutely hate producing waste. I feel really anxious about where is this going to end up?
yeah.
So, you know, old clothing that really cannot be fixed anymore. You know, it's not share and repair, it's not mending it. What can be done with these? You know, is it better to put it into landfill or to burn it or to send it to Africa? Of course, that's, I mean, I don't want to do that either. I don't want to do any of that.
I mean, for years, there was this dry tomb approach for landfill. It would be, you dry tomb it. You stick in the ground, completely cover it on every side. No water can get in, it'd be completely dry, which meant there's no biological activity, so it would just sit there. It's not producing anything, it's not causing anyone any problems, but it's still sitting there, and it will sit there for hundreds and hundreds of years. They're moving away from that now, because they're saying, well, it's great, but, you know, what if the line is split, or, you know, you want to dig there or something, you know. So, and that's the other thing, we've been chucking away very valuable resources for, you know, the last couple of hundred years, and we're now digging them back out. So landfill mining's becoming a thing, you know, it's not massive in the UK yet, but it's now a thing. They're going back, they're digging up, they dig through this, they can take the metals out, plastics, you can take plastics out and burn them.
They've been doing that in Africa for centuries.
Yeah, exactly. So, yeah.
I wanted to know the longevity of the plastic lining and the capping. To begin with.
Yeah, I mean, I think they quote sort of 200 plus years, because when they put the base liner in, they, you know, it's very well engineered. So, you know, they just put it down on the ground. You know, the cells are very, you know, smoothly engineered, and they put down like sand barriers, so nothing kind of pokes through.
Okay, so nothing sharp can pierce through.
Exactly, can't pierce through. It's also an anaerobic environment, so things kind of, you know, like when they sometimes find bodies in peat bogs that are 5,000 years old, you know, things actually survive quite well in that environment. It's obviously quite a chemically rich environment for all the leachates and things coming through the waste. And you've got waste which does poke through and does go up. So when they design them with like a certain amount of leakage. And underneath the liner, there will be drainage, so like you know, gravel or something, or sometimes actual pipes, and anything that comes through, because they do leak, and even when they're brand new, when they seal the sort of different sections together, they test them, and then they test the tests, and they test tests, but there's always a few leaks. So they expect them to leak, they just don't want them to leak too much. Top liners, it's a bit easier, because obviously you can just take it off and replace it.
But then you have to replace everything that you've dug up as well, like the trees, the grass.
Yeah, no,
ditches,
of course,
the
yeah.
houses.
Well, so that's, you know, when I say planting trees on landfill, you know, again, I'm not a horticulturist, but, you know, roots go to a certain depth. So, and you need a certain depth of soil for stability for the trees, and so they can draw up enough nutrients. But what you don't want is be punching through, you don't want roots punching through caps. And then I said they're plastic, not always plastic. Sometimes they're engineered clays and things like that. So they're not always plastics. You know, a lot of places actually don't put plastics on because they want the gas to come out. They want it to oxidise in the soils. So, yeah, so if you're planting trees, you're probably planting them on old sites which have no engineering at all. There's no bottom liner, no top liner. So.
And so what's the future for these landfill sites? What's going to happen with this tombed waste? Are we just going to gradually landfill the whole of the country?
So part of the landfill directive is operators have to have like a fund, like a long-term fund. They have to invest, almost like a pension for the landfill, so that, you know, even if the company goes bankrupt, there's a fund which is kept to maintain the integrity of the landfill. And that varies, but it can be up for a couple of 100 years. So they have to have enough money to say, people will be looking after this for the next couple of 100 years, which is all very well, but
Yeah,
we
but
know
that's just
from
covenants.
research that 200 years is not enough. You know, you can dry in, you know, in the UK it's quite wet, but imagine somewhere like Australia or, you know, sub-Saharan Africa where it's very dry, and it would be there for thousands of years. So the drive, and this is what I've been working on when I'm not working on methane, is how can you accelerate that clear up? How can you take this tomb of waste, what can you do to it now to reduce that 200, 300 year legacy down to like 20 years? Spend that money that's been put aside, spend it now, spend more, just get it done now so you can walk away. And that's what the Dutch have been doing. That's, you know, they changed legislation so they could do all these tests on their sites, and there's various things you can do. You can blow air in to accelerate degradation, recirculate fluids and things, and yeah, that's quite effective, but it's expensive. So to go to an operator and say, well, spend the money now or spend in the future, and they'll say, I will deal with it in the future.
Yeah, so are these landfill sites going to be like recycled landfill sites then, with just an endless amount, and then they'll have 20 years being fallow, digesting, and then you open them up again or excavate in order to dig more waste down?
Possibly, yeah. I mean, if it's a useful resource, and because the cost of energy went up so high, digging out plastics on landfill and then burning them was actually seemed quite sensible. But even if you do that, if you incinerate wastes, dig up, recycle it, there's always residues. You know, you burn the waste as ash, you've got to do something with the ash, and at the moment they landfill it. So there's always going to be landfill. And yeah, again, to answer your question, I don't think anyone really knows what will happen. Yeah. So.
So the soft plastic is now being recycled. Mm-hmm. Is it, or is it not? Where is it going?
I don't know. Yeah, they collect it, but where it goes. I worked on a site years ago before I did this research, and they just opened a big recycling facility, like a big automated recycling. So the trucks would come in, dump the rubbish from people's houses. It went up for all these conveyor belts and those pickers and all these fancy machines taking out different plastics and metals and big magnets, and there's all the processes. Theresa May turned up to open it. She cut the ribbon. The BBC were there. It's this big fancy thing, and I was working there. And what I saw, which no one else saw, is they bring the trucks in, dump rubbish, pile it on these conveyor belts. We go through this amazing system, and it will come out the back. They put it back in the truck and then drive up and down landfill it. So because there was no market for it. You could recycle the goods, but it would just pile up. It'd just pile up and pile up. So we found a market. We were selling it to, giving it or selling it to China, and they were sorting it. But they're now like, well, we don't need it anymore. So it just piles up there, you know. But we just made it someone else's problem.
Yeah, it's gone to Malaysia for a long time, hasn't it?
Yeah.
Yeah.
So, yeah.
Yeah, I think that we need an.
If you like the man on the Clapham omnibus, what are the three things that average person could do to reduce their personal greenhouse gas emission? I mean, if we gave up dairy, went vegan, stopped travelling and turned the central heating off, would that crack it?
Yeah, I mean,
I'm saying that with a plastic bottle at
Yeah, well,
thing.
exactly.
I swear
we
I've
have.
only bought one this year and it's right there.
Yeah, that's why I use this bad old thing.
It's kind of ironic that I have it on me this evening, but would that be a meaningful thing to do?
Yeah, it would. Yeah.
Or would it just
and like
be
the
like
impact,
planting trees,
the impact in the UK would be fairly small. But if everyone did it, if that spread around the world, then of course it would.
I mean if if you look at it as what one person could do, that if they all did it across the world, that would.
Well, flying is terrible.
Yes.
We kind of know that.
So don't travel.
But it really is, and I didn't show the figures from transport, but it was all going down.
I saw that.
And then we had COVID, and it just dropped. There's virtually no emissions from transport, and it's just going up and up and up and up. It's going through the roof. People are flying more than they ever were.
Yeah, I have two daughters who are environmental lawyers, and they fly everywhere, and I think it's just the massive hypocrisy of it, I think, is incredible.
It's crazy. It's, you know, so flying's bad. So a personal thing you can do, don't fly. Well, people sort of have to fly a bit. Like my wife's from Ireland, she wants to go and see her family. You know, how does she get there? There's no...
Train, ferry?
Drive, but then that's almost as
Don't
bad,
go
that
very
distance.
Get over it.
So,
Same
with Skype,
thing,
yeah.
who wants to go there anyway? But,
Well,
yeah.
it's quite nice.
So travel...
So travel's not good. So
Heating,
reduce travel.
and food.
And, well, yeah, dairy particularly. Dairy
Yeah.
is like, of the food things, dairy's bad, because we're using so much land just to maintain dairy.
It's a massive
Just to feed the
pollutant.
animals, yeah.
Yeah. It's massive.
You know,
pollutant.
and that would be much better used for other sources of food, like food for us. Like we're feeding animals, which a few
three
people
things,
eat. You know,
really.
not everyone eats those animals, and then the dairy. You know, so dairy's not good. Yeah, it has to go down. You know, but again, don't get rid of it. Like we have a whole industry, we can't just completely get rid
Well,
of
you
it.
could
You know,
actually, couldn't you? So,
I don't know. I walked past a cheese shop
food,
earlier, and I
travel
was quite
and
intrigued.
heating.
You know,
Thank
so,
you,
yeah.
thank you.
Okay, we're coming up to 9 o'clock, so this is going to be the last one.
Okay, no pressure. So my question would be, given everything we've heard, is it possible for waste management to reach net zero by 2050?
No.
Okay.
Okay. No. I think it's such a long-term legacy in waste, and that graph I showed of the gas curve where it takes 20 years and it just goes on forever. I don't know. You know, you could spend a fortune engineering sites to oxidise all that gas, collect it all, but that's not going to happen in 25 years. So, no. I think you just have to keep going down. It's going down slower and slower every year, and there'll be a point where, you know, because even if we give up dairy and we give up plastic bottles, we can't give up everything. We still want to build things and, you know, get on with life. And although we think it's a good idea, lots of people don't care at all. So, yeah. 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 Yeah, and the ash, it's from the incinerator ash, you know, they're desperate to find something to do with that. And one they're looking at as you know, road material. So
There is a very simple thing that we can do to help, which is to make things last longer. I'm going to call a halt to this because it's 9 o'clock and the people who work here have to go home. I think we've had a very interesting discussion, and I really like to thank Tristan for actually ranging much more widely in the discussion than he probably thought he was going to have.
yeah, so I hope it wasn't too much.
No, it was great. It was great. And actually, I learned something today which really surprised me. I did not know why I wasn't allowed to throw away plasterboard at the recycling centre, and now I know. And by the way, actually, hydrogen, I'm a biologist, and I know that hydrogen sulfide is actually a really poisonous gas. It's almost as poisonous as hydrogen cyanide. Luckily, you could smell it from a long way away, so nobody is ever poisoned by accident by hydrogen sulfide because it smells so terrible. But don't throw plasterboard in the general rubbish. So anyway, thank you very much, Tristan.
Thank you.
Very interesting.
Okay, thank you.